Greetings everyone. I'm going to be presenting a paper titled A Dictionary Running Approach for Noise Robust Image Reconstruction in Raw Field Magnetic Resonance Imaging. I am Emmanuel Ahishakiye from Mbarara University of Science and Technology in Uganda. Magnetic resonance imaging is a safe medical imaging modality that is non-invasive. It does not produce harmful rays because it just uses magnetic fields during imaging. However, conventional or high-field MRI scanners are very expensive to purchase, operate, and maintain in developing countries. And due to these limitations, many people in developing countries do not have access to MRI technology. And to address these challenges, teams from Mbarara University of Science and Technology in Uganda, Leiden University Medical Center in the Netherlands, Delft University of Technology in the Netherlands, and Penn State University in the United States are working in developing affordable, portable, and sustainable raw-field MRI scanners. And the major aim is to diagnose children with hydrocephalus in Uganda. Hydrocephalus is a condition where there is too much accumulation of cerebrospinal fluid in the head, and it causes the head to expand. The head becomes big. I think you have ever had or seen children with such a conditions. So the figures here shows the MRI prototypes that are currently in development. The one at the left is the prototype at Mbarara University and Penn State, and the one at the right is a prototype at Leiden University in Netherlands. And the major limitation of these MRI prototypes is that they are characterized by low signal-to-noise ratio, and this has high impact on the final image. Also, images that are obtained by these prototypes, they tend to be noisy, and on addition, they take a long time to generate an image. A case, the prototype at Leiden takes more than 16 minutes to scan an object. This study is incremental in nature, and it seeks to integrate image reconstruction and noising algorithms. We want us to come with one algorithm that has the potential to do a reconstruction step and also doing a denoising as the algorithm, the software runs. The major objective, therefore, is to implement this algorithm that is suitable to address the challenge of raw signal-to-noise ratio that is characterized by raw-field MRI systems. So we propose to use a two-level Bregman method for image reconstruction. This method has two parts. One part is to estimate the recovery of the image, and the other part is to calculate the dictionary and the sparse coefficients of the image patches. And for the denoising part, we want to use an algorithm called simultaneous code word optimization, in abbreviation SIMCO for the denoising part. This SIMCO, for it updates the atoms in the dictionary at once, and it has been found that it is far better or faster than the popular algorithm called KSVD, because KSVD updates atoms individually. So this is the proposed algorithm. The first part, as you can see, you initialize the algorithm, and the first while it's the reconstruction working, and when it reaches to step 13, as the reconstruction is going on, then you reconstruct, you denoise an image, and the result will be a noise-free reconstructed image. Now, when it comes to evaluating our results, we used peak signal to noise ratio and reconstruction time. Reconstruction time is the time it takes the algorithm from initialization to giving out of the image. Peak signal to noise ratio is measured in decibels and is computed as the ratio of the peak intensity value of the reference image to the root mean square reconstruction error relative to the reference image. And peak signal to noise ratio is considered as the image quality measure and has been used a lot as a performance metric in compression and noising tasks. However, peak signal to noise ratio does not represent perpetual visual quality, which can be assessed by human observers. Here this slide shows the results, the visual quality after running our algorithm for 20 iterations. And here we were using a phantom on the left, and we did an analysis of the performance in comparison with other state-of-art algorithms. So here, this B is the reconstruction done using a popular algorithm called TBMDU. It is referenced in the article. You can see it for details. Then this part C also was reconstructed by an algorithm called DLMRI. This algorithm has been used a lot as an algorithm for comparison in many papers. And this part D is an image that has been constructed by our algorithm. As you can see, our algorithm has potentially removed the noise like artifacts here. Then we said, let us see now the reconstruction time and the peak signal to noise ratio after 20 iterations. And as you can see, our proposed algorithm has at 3.8 decibels. We did several experiments and we calculated average. And you can see DLMRI has 30, while TBMDU has 30.2. And for the execution time, you can see that our algorithm is not fast slow, but a bit slow when you compare with the two algorithms. Okay. Then we tested also on an image that has been produced by a high field MRI scanner. And as you can see on the left, this is the original image. Here, this is an image constructed by TBMDU, and this is an image that has been constructed by DLMRI, and this is the image that has been constructed by our proposed algorithm. And also, like as in the noisy phantom, you can see that our proposed algorithm has higher peak signal to noise ratio compared to the two algorithms. However, it also took some more time when you compare with the two algorithms. And therefore, what we can deduce from the results is that our proposed algorithm is better. It works well when the input signal is a bit noisy when you compare the results with TBMDU and DLMRI. However, it is slow compared to the two algorithms. The algorithm also was not compared with deep learning techniques. This is because these deep learning techniques have high computational complexity and they require large training data sets, which were not available for us. And the results demonstrated that our proposed algorithm is effective in removing noise during the reconstruction step. In conclusion, therefore, we have discussed a comprehensive-based image reconstruction algorithm that combines both reconstruction and noising, and the results from the experiments demonstrated that our proposed algorithm performed well, especially when the input image or signal to be constructed is noisy. Also, we can conclude that our proposed algorithm can be applied in low-field MI scanners that are coupled that are characterized by producing noisy image, and therefore it can help to improve the quality of the images. And how far we have gone with our project. We are currently replicating the MRI devices at MAST, the one at Penn State and the one at Leiden, and we are unifying our software because we have researchers at the Delft University of Science and Technology. We have researchers at Penn State, we have researchers at MAST working on image reconstruction software. We are unifying it to be one so that we can deploy it in our algorithm. And we acknowledge Mbarara University of Science and Technology, Children's Hospital, Penn State, TU Delft, and RUMNAC. Thank you.